Hi everyone, I'm Taylor Sloop. Thank you for joining me today, and I will be discussing the effects of controlled porosity on the dynamic compression and tensile failure of additively manufactured 316L stainless steel. So I'll start off with going over the motivation and objectives for this work. So the motivations stem from the fact that steels can be additively fabricated with microstructure containing intentional porosity, and this can be random or controlled porosity. So an example of this is in the figure in the bottom left corner, where you can see the randomly placed intentional pores that are spread throughout this sample. Additionally, process-inherent porosity, such as lack of fusion pores, has been effective in shockwave dissipation and swell strengthening improvements in additively manufactured materials in the past. So based on these motivations, the objective for this work centers on correlating the fracture behavior of AM316L stainless steel to pre-existing intentional pores of specific size and configuration, as well as isolating the effect of the presence of these pores on shock disruption and stress dissipation caused by the pore collapse or stress concentration in the immediate vicinity of these pores. So, to investigate these objectives, plate-on-plate impact experiments were conducted in a single-stage gas gun. And these were used to investigate the spall failure of pore-containing materials. So the same setup was used for all of the different pore configurations and sizes that were considered for these experiments. A flyer and target assembly were set up with wrought 316L stainless steel, and multiple samples were placed in each target assembly to keep the experimental parameters as similar as possible for comparison. Additionally, multiplex PDV, or photon Doppler velocimetry, was used in each of these experiments as well to collect velocity profiles at different locations on the back surface of each of these samples for both pore-containing as well as fully dense materials. So now I'll walk through what shockwave interactions are occurring within our samples for each of these experiments. So to start with, on the left is an XT diagram, or distance versus time diagram. So the x-axis is our distance, time is on the y, and we can see the flyer plate, or the thing that we're shooting in the gas gun, on the left, with our sample on the right, which is stationary. So using this graphic, we can see what's happening with the shock waves in both the flyer plate and sample over time. In the top right, we have a graphic showing what's actually happening in the gas gun. So this is looking horizontally into the gas gun. So you can see the flyer on the left again, and the sample on the right. And in the bottom right is an example of a free surface velocity profile. So this is the velocity profile that we can collect from the PDV that we have analyzing the particles on the back surface. So essentially, we're measuring the velocity of the particles on the back surface of our sample so that we can see how the shock wave is propagating through the material. So initially for these experiments, we shoot the flyer plate towards our sample. And when the flyer plate reaches the sample and impacts it, we now will have shock waves that will move away from this impact into both the flyer plate and the sample. And because we've selected the flyer plate and the sample to be the same material, we know that these shock waves will move at the same velocity. So the same distance will be traveled in this initial distance. And when this shock wave reaches the back free surface of the flyer plate, it's now going to interact with air. And when this interaction happens, it's actually going to now rebound back into the flyer plate. So you can see that this is now rebounding back towards the material as the shockwave in the sample is continuing to move towards its back free surface. But now the same thing is going to happen in our sample as it's reaching that back surface. So in our velocity profiles, we can now see that we're reaching a velocity plateau as that shockwave is now reaching the back surface. It's bringing those particles up to its maximum speed. So now that the shockwave has reached this back surface, it's now going to rebound back into the sample in the same manner that we saw it doing at the back of the flyer plate. So now both of these shockwaves are moving towards each other within the sample. So as this is happening, we start to see the shockwaves move towards each other and then eventually cross. On our free surface velocity profile, we do see that the velocity starts to drop as the shockwave moves away from this free surface and back into the sample. And now these shockwaves have reached each other and will cross over each other, which will create a region of tension in the center of our sample. So as they cross over each other, we now have a shockwave that is moving back towards the free surface, which will lead to an increase in the velocity as that flyer shockwave moves towards the back free surface. But we've now also created a region of tension in the center of our sample. So you can see that in this gray region. So as those shockwaves have crossed over each other, it's now pulling apart. And if we're applying enough tension force, we'll have failure in this region. So it'll have voids forming, growing, coalescing, depending on how much damage this sample will sustain. So this region is what we call the spall region, and it's generally placed in the center of the sample, which we do by specifically choosing the flyer plate to be half the width of our sample. And after this spall region is formed, if we have damage, we will now have these shockwaves rebounding back and forth from the back free surface of the sample to the spall region and back and forth and back and forth. And we see this as ringing that can occur in our velocity profile. So that's what this continuous oscillation afterwards is. There is some other information we can gather from our velocity profiles that can be very helpful to compare between different materials or the same material with different pore configurations. So one of these values is our Hugonio-elastic limit. So we can measure this on our velocity profile looking at that initial change in slope. So it's circled in red right at the very bottom. And we can calculate our Hugonio-elastic limit using this equation where we consider the density, the longitudinal sound speed, and this velocity value that we gather from our free surface velocity profiles. And the Hugonio-elastic limit essentially allows us to differentiate between when we're moving from elastic to plastic deformation. The other piece of information that's very helpful from this plot is that we can also calculate our spall strength. So we do this by using the distance between the velocity plateau and that first minimum. So using that value as well as our density, bulk sound speed, we can calculate the overall spall strength for our material. So now we'll jump into some of the actual experiments for this configuration. So the influence of pores was investigated with 3 different primary configurations. So we'll look at single pore, cross pores, and stacked pores. So single pores is just 1 pore in the entire sample. That's pretty large. And then the cross configuration has 5 pores that are all spread within the expected spall planes. So these are perpendicular to the impact direction. And then the stacked pore configuration is looking at 3 pores stacked in the direction of impact. So these are parallel to the impact direction. And then from all these configurations, we'll go back and compare to a many pore sample, which was randomly placed, which has some combination of the single, cross, and stacked configurations throughout the sample. So we'll start by looking at the single pore configuration. So the effects of a single pore in the center of the sample with respect both to diameter and height was investigated at a high peak stress of greater than 7 gigapascals. You can see that these pores were cylinders, as you can see from looking at the top and the side view, and 3 different pore sizes were considered. So we looked at 200 micron, 350 micron, and 500 micron pore sizes for each of these different single pore configurations. So we'll start off by discussing the velocity profiles that were collected for each of these samples. So in black in each of these graphics, we have the fully dense material. So this is a sample that does not have any pre-existing pores placed in it to compare to the pore-containing samples. And on each of these pore-containing samples, there were multiple PDV probes placed on the back surfaces to calculate a velocity profile for different distances from these pre-existing pores to hopefully isolate the effects of the pore farther from the pore where we expect there to be less effects from the pore versus right next to it. However, there's very little differences that can be measured between the fully dense or any of the locations on these pore-containing samples for any of these velocities or any of these pore sizes, 200 micron, 350 micron, or 500 micron pores. There are some variations, but due to the heterogeneity that is always present in additively manufactured materials, these differences can't specifically be attributed to the presence of the pre-existing pore. There are some differences in the rise time, so which is from the start up to that velocity plateau that we discussed earlier, as well as slightly different slopes after that velocity plateau and then on the next rise. There are some differences, but these can't be specifically attributed to the presence of the pre-existing pores. Rather, they could be due to just general heterogeneity present in the materials. So the PDV doesn't really show all that much of a difference between the 200 micron, 350 micron, and 500 micron pores. But when we cross-section these materials and actually look at the damage plane, we see a very big difference when comparing these samples. So we'll start by looking at the fully dense material, which is in the top left. So we see that there is extensive damage in the spall region, exactly as we'd expect there to be. So there are some large voids forming, which you can see circled, an example of circled in green, as well as some more coalesced ellipsoidal voids. So these are voids that have now connected to each other, which is exactly what we would expect in the fully dense material. And using image analysis, we were able to count up the number of pixels that are included in these pores and calculate the overall pore area to be 0.49 millimeters squared for this fully dense material. So now we'll move on to the 200 micron sample, which is the top right. You can see the estimated location of the pre-existing pore is the black line right in the middle, but the pore has been fully collapsed for this configuration. And again, we see this large void circled in green, but we see a lot of void coalescence across the entire sample. So there's a lot less void growth, more of a move to void coalescence. Additionally, there's a little bit more damage overall, 0.54 millimeters squared damage across the entire sample. So we see some change in what that damage looks like for the 200 micron pore, but we still see about the same amount of damage. But then we move to 350 micron pores in the bottom left, and we see that there's a lot less damage. So it's only 0.36 millimeters squared. So we see that that coalesced region is still kind of similar to what we see in the 200 micron pore. There's a lot less of the large voids, and that actual coalesced region is thinner. So there's overall less damage as we move into this bigger pore, but it does seem to still be a little bit different than what we see the damage profiles looking like in the fully dense material. But when we get to the 500 micron pore, now we start to see a very big difference. So to start off with, the pre-existing pore is not fully collapsed. We do actually see that, and you can see it circled in red in the bottom right. Additionally, the region around that pore is much more in the void initiation phase rather than void growth and coalescence. So it's a very, very small voids compared to the very large voids that you see in the void in the fully dense or even in the other pore containing samples. And this is in the region around the pore. But as you start to move farther away from the pore into the regions boxed in green, we revert back to this type of damage we see in the fully dense samples with a lot of void growth and start to see some coalescence between them. Overall, we see a lot less damage as well with only 0.18 millimeters squared. So as we increase pore size, we see a change in how the damage is forming as well as a decrease in damage overall. And we see this continuing when we look at EBSD. So the top image is SEM, the middle is EBSD or electron backscatter diffraction, and a kernel average misorientation map is at the bottom. So in the EBSD, what's important is that we see that there's a lot of these black regions that are beyond what we see for the pores in the SEM image. So this means that there's lots of regions that we were not able to map, most likely because of too much damage in that area. So we see that there's a lot of damage concentrated right around the pre-existing pore that doesn't necessarily correlate to actual void growth yet. And we also start to see a lot of misorientation, so this bright green region farther away from the pre-existing pore, but we don't really know what's happening right around the pore since we aren't able to map it. So this suggests that the damage is concentrated right around the pre-existing pore instead of being spread throughout the small region as we would expect to see, which we can compare to the 350 micron pore and see that, yes, there is a lot more consistent damage across the entire sample, a lot more consistent kernel average misorientation across the entire sample. We do also see twinning, which is expected in our small region, but again, it seems to be concentrated right around the pore, which we can't seem to map for this one. But then there is extensive twinning when we start to move farther away from the pore. The same thing we see in the fully dense material, whereas it's spread very consistently across the 350 micron sample. So overall, as we increase the pore size, we start to see less small damage. And then also there's a higher concentration of damage in the immediate vicinity of the largest pre-existing pore. So now moving on from this, we'll start to look at the cross and stacked pore configurations. So again, this time we looked at 200 micron and 500 micron pore sizes with cross configuration placed in the small region, and then the stacked pore configuration is stacked in the direction of impact. So again, for these, we don't really see much of a difference in the PDVs looking at the cross or stacked configuration. So this is for the 200 micron pore. There are some slight variations, but these can't be attributed specifically to the pore configuration or the pore presence of the pre-existing pore, because it could, again, just be some of the heterogeneity that is often present in these pre-existing samples or in these additively manufactured materials. And this is again true for the 500 micron pore size, although there does seem to be more differences. It is difficult, again, to attribute them specifically to the pre-existing pore, especially because these differences are not a consistent trend across these samples. So again, the PDV isn't particularly helpful when differentiating these samples. But what is very interesting is that there is a very big difference, again, when we look at the cross-section. So the top image is our fully dense sample. It has about 0.32 millimeters squared damage. It's spread very evenly across the sample, exactly what we would expect to see for a fully dense sample. But now we'll move into the stacked and the cross configurations. And again, these pores are not fully collapsed for the 500 micron sample. But this time we see that damage come all the way up to the edge of the stacked pores, which is very different than what we saw for the 500 micron single pore, where there's very little damage at all immediately around the pre-existing pore. There's also a little bit less damage than the fully dense, but still quite a bit of damage when we're looking at the stacked configuration. The cross configuration, however, has less damage in the immediate vicinity of the pore, although it does have more than the single pore configuration did. So it does overall have less damage, a little bit more in the void initiation rather than growth and coalescence that we see in the stacked and fully dense. So for the 500 micron pores, the cross has the least damage, but both of these configurations have more damage than the single pore example. But this trend flips when we start to look at the 200 micron sample. So again, the fully dense sample, 0.32 millimeters squared damage. But this time we do actually still see a little bit of the 200 micron pore sizes in the stacked configuration after impact. But there's less damage overall in the stacked region compared to the 500 micron stacked. We do have some damage coming right up to the sample, but overall there's less damage in this region. And the same holds true for the cross configuration again. And again, the cross configuration does have less damage than the stacked configuration, although it's less of a noticeable difference for the 200 micron than the 500 micron. And again, this is very different than the 200 micron single pore, where there was extensive damage across the entire sample and looked very similar to the fully dense material. So the presence of multiple 200 micron pores is more effective at dissipating stress and shock than the 500 micron is. So overall, multiple pores have more damage than the single pore of a comparable size for the large configuration, and the stacked configuration has more extensive stress concentration with more damage than the cross configuration. So when you start to add more pores, a smaller size seems to be more effective at limiting the damage, but it does depend on your configuration. Stacked pores, so multiple pores in the direction of impact, has more damage than we see for the cross configuration. So now we'll consider the many pore configuration. We'll see a combination of both the single pore, cross pore, and stacked pore throughout the sample. So this sample had many pores placed throughout the sample. They were randomly placed, so some of them are grouping together. As you can see in figure B, there's multiple pores stacked together. So this is a much larger pore than anything we considered in the single pore configuration. And you can see in the immediate vicinity around it, circled in yellow, in figure B, there's very little damage right around the pores. But when there's just one pore, there's much more damage, especially when it starts to be stacked, as you can see in the bottom portion of B. So we do see that still trend of with a very large pore that's isolated, like the single pore, there's a lot less damage around it. But then in figure C, you can see more of the cross configuration, where there's multiple pores all near each other, and there's less damage in their immediate vicinity, circled in yellow, compared to the regions away from the pores, circled in red, where there is more extensive spall damage. So we see this consistent trend between the single, stacked, and cross configurations that we isolated before is consistent when we start to add more and more pores to our samples. So we do see a combination of the effects from the single, cross, and stacked configurations in this less controlled random porosity sample. So regions with both stacked and the cross configurations in the same plane exhibit some intermediate levels of damage, whereas larger pores printed together and in isolation have less void initiation and growth in their vicinity. So we see the continuation of the trends that we identified and isolated with the controlled configuration growing into the many pores in the random configuration. So future work should focus on isolating the complicated effects of combinations of pore configurations. So more modeling work on the pore collapse method and range of influence would be particularly valuable, as well as a targeted investigation of the extensive stress concentration in the immediate vicinity of the pre-existing pores. So especially looking at that 500 micron pre-existing pore, where that damage is so concentrated around it that it's hard to isolate after the experiment. It would be helpful to have modeling and more isolated experiments specifically looking to investigate this stress concentration. Additionally, an investigation of the effect of the trapped powder in the pre-existing pores would be particularly beneficial. Since this is laser powder bed fusion, there is powder trapped inside, and how does that powder affect the shock propagation would be very interesting. So now I would like to acknowledge the funding support and thank my lab groups for all of their support. Thank you and have a good day.